Welcome to our talk on workload over time, modeling in a cognitive architecture. My name is Nele Russwinkel, and together with Preuss, we want to present this work. We are from the Chair of Cognitive Modeling and Dynamic Human Machine System at the Technical University of Berlin. I want first to shortly go over the multi-dimensional concept of workload and give a short introduction to cognitive architectures because we did our approach in this relation, and then Kai Preuss will introduce the approach and an example study, and we will discuss the results in the end. For mental effort, according to Shenhav, this can be defined as a construct that mediates between the characteristics of a target task and the subject's available information processing capacity, and the fidelity of the information processing operations actually performed. So here we have the first two factors, task characteristics and cognitive information processing capacities. These determine what level of performance is attainable, and this we can, I think, quite well capture with our cognitive modeling approach. The second part, the intervening processes that determine what level of performance will be realized, that is has a lot of facets, and that might be something that we should discuss in more detail later on, what all these intervening processes are and which are really the ones we can explain and which we can't. So we have some parts of that we can explain, and we can predict response times and accuracy, but I think there are a lot of other aspects too. For workload, here follow the multidimensional concept according to Manzai. We have a lot of different dimensions that play a role and that we should focus on if we want to understand this concept. Workload is a result of a complex interaction among several variables of an individual and a task, according to Koffer and Dorchin. Here we already see that this is not just the task characteristics and the cognitive processing capacity. We have different variables here. We have different workload using cognitive processes, and also the task is more an interactive task. So that could be a very relevant part here. Even for the same task, which is quite interesting, the same individual, the performance, effort, and physiological arousal may change or remain stable depending on the strategy used to accomplish the task. This, according to Hockey, a really important point. So such models should also incorporate the strategy that the individual uses, which is difficult because sometimes the individual can't really report what strategy they use. So that is not a very easy thing to do. And this actually sums up to the final point that workload is a multidimensional concept because we have a number of different potential workload patterns. Also, the measurements are not always measuring the same, so we probably have different kinds of workload that all are combined with this one term, and they cannot be fairly represented by a single indicator. So we would need to have an approach that has both sides. So on the one hand side, captures different facets or dimensions of this workload concept, and on the other hand, give us some relative idea about, is this higher workload or is it lower workload? To give you a better idea about the information that has to be considered here, I have an example of complex human-machine interaction. So for the pilot, there's a lot of visual processing going on for displays, environment, motoric actions, of course, memory for what situation I am in, what is evolving, what should be done in a specific information, auditory processing and verbal for communication, but also if there are alarms going on. And we have expectations. So what might happen when I do this action, and what normally happens when there is some thunder coming on, or dark clouds, or whatever. And we have a dynamic environment. So this is just such a complex combination of different capabilities. So what we need is a modeling approach that captures different modalities, is modular in nature. And this is why we used the Cognitive Architecture ACT-R. So here we have different modules and cognitive processing units that have a restriction in capacity. So for example, for visual processing, for motor processing, we have also declarative memory. Information can be encoded and retrieved, imaginal, we can integrate information. We have a goal module. These are related to brain areas that also have these functional processes. And we have production rules that can exchange information between those modules. For workload, it might be interesting to look at how many modules are active at a point in time, and also what modules might have a stronger impact on workload than others. And for this, I want to take over to Kai Preuss.
Hello, everybody. In the following slides, I will present our experience of workload estimation in cognitive models. We are using an approach published by Yo and colleagues in 2012 called Quantitative Prediction of Mental Workload with the ACT-R Cognitive Architecture. In theory, this algorithm allows the computation of cognitive demands during a task in arbitrary time steps. Module activity during trials is generated by ACT-R, with each individual module assigned to a weight. These were predetermined by evaluating NASA TLX scores of participants in a memorization, a visual manual, and a menu selection task. Activity of sensory and motor modules is multiplied by 1, so maintaining their face value. Procedural module activity is multiplied by 2, and activity by imaginal and declarative modules is multiplied by 4. The activity is partitioned into several time steps, and during each of these time steps, module activity is sampled and aggregated into a weighted sum, resulting in a mental workload value. This value depends on the chosen time frame, the number of modules, and of course the task at hand. So workload values from several time frames represent snapshots of estimated cognitive effort during the task, which can in turn give insight into cognitive demands of specific situations during task solving. For our purposes, we used a simplified version of the Sternberg task paradigm. A Sternberg task consists of a series of letters presented to the participant, which is followed by a prompt to decide whether a target letter was included in the sequence of letters. This paradigm has a long history for assessing an individual's mental workload during task solving. It clearly separates cognitive demands into a visual attention and retention period on one hand, and a memory retrieval and motor reaction period on the other. In addition, it easily lends itself to having additional distraction tasks added for increased cognitive demand. Our task design presented letters for 1.2 seconds, followed by a 0.2 second pause, followed by either another letter or the target prompt. We varied the length of the letter sequence between 2 and 7 letters at a time. As a distraction task, we included an auditory discrimination task. In one within subject condition, participants were presented with 2 subsequent tones at a time at fixed intervals during the main task, and were instructed to answer as quickly as possible whether the second tone was higher or lower in pitch than the first. This task is to be performed in parallel, so it requires additional resources for auditory and motor processing. In the control condition, no additional discrimination task was given. Behavioral and pupillometric data were acquired from a previous experiment with a variant of the Sternberg task conducted by Laurenz Kroll and Klaus Grammann of our partner chair for biological psychology and neuroergonomics at the TU Berlin. This data was used to see if markers of cognitive effort correlate with simulated mental workload estimates. Finally, we were interested in seeing if a longer letter sequence and/or the presence of a distraction task would increase the workload. Pupillometric data is thought to be reflective of cognitive effort. Based on this idea, we were especially interested in seeing what changes in the actual cognitive effort it indicates and how mental workload estimates based on cognitive modeling compare. The pupillometric data was analyzed as part of a master thesis by our student Lou Conradi. For our purposes, we will look at the average pupil sizes during different letter sequence length and whether a distraction task was present. On the left, we see absolute pupil size averaged over the trial and aggregated over all trials and subjects in relation to sequence length. While the number of presented letters seems to have no effect on pupil size, it is in fact dependent on the presence of a distraction task. Pupil size in general is significantly smaller during tasks with auditory distraction. The right graph shows pupil size change relative to its size at the beginning of the trial. As before, an effect of sequence length is unclear and proved to be statistically insignificant. However, pupil size tends to decrease more strongly during distraction tasks. The underlying processes of our model are shown in this flowchart. Production rules, here as blue blocks, look for the presented letter, attend and encode it, and repeat that as long as new letters are presented. Once all letters have been shown, the queried target letter is compared with all memorized letters. If a match is found, or if all retrievable letters have been compared, the appropriate answer is given. For the auditory discrimination condition, 2 tones of different pitch are played in regular intervals, which the model detects and compares to answer which tone was higher. Production rules for processing this distraction task are shown on the right. Both main and side task processing are attentive in parallel and are not hard-coded to be prioritized over one another. The processes are underlaid by colors representing the module primarily involved in its execution. ACT-R's modular approach offers distinct modules for visual, oral, declarative, or motor processes. These modules can be active in parallel, while the production rules are processed in sequence. During task attendance, the mental workload according to the computation by Yo and colleagues is computed for all model processes. For demonstration purposes, let's look at a qualitative example of our model results first. These plots each show data for a single Sternberg trial consisting of 5 presented letters. The left side shows plots for the Sternberg trial without a distraction task, while the right side shows the audio distraction condition. The upper plots show the simulated mental workload over time. The lower plots show the activity of ACT-R's modules. At a glance, module activity for the distraction task is more frequent, processing both visual and auditory information. An interesting point is the high frequency of the production rules for the distraction task condition, which implies a possible bottleneck in cognitive processing with high task demands. Also of note is that workload during tasks without distraction spikes at the end, caused by a memory retrieval process with subsequent motor action, but does not spike during the distraction task condition and is upheld at a high level during most of the task. Here we see differences in mental workload during single trials, each in a different condition. Solid lines represent a sequence length of 2 letters, while dashed lines represent 7-letter sequences. The yellow and red lines indicate a distraction condition, while blue and purple lines show a trial without audio distraction. We see a similar pattern as before, as trials without distraction tasks generate less mental workload overall, with spikes at the end for memory and motor processes, and trials with distraction tasks exhibit a higher, continuous overall workload. To summarize, the mental workload measure proposed by Yo and colleagues makes reasonable predictions about the cognitive workload during individual trials. Differences in experimental conditions are reflected by the value and show promise as a reflection of cognitive demand changes during a trial, instead of formulating a single value after the fact. As of now, the resulting workload value for each time frame is hardly standardized. The resulting value can be an arbitrarily high number, which is highly influenced by the chosen time frame size, module structure, and model. Furthermore, the original paper was unclear about the effect of module errors, for instance, a failed memory request on workload. For our computations, we assumed a drastic effect of potential errors, resulting in double the workload compared to regular module activity. In the future, we hope to be able to compare this approach to existing other measures of mental effort to better validate this approach.
Thank you. Well, in the future, we plan to conduct more examples of our approach and compare them with participant data, also with different measurements of workload, like nasal-telix, pupil dilation, and so on, to get a better picture of what, how good those different measures and predictions relate to each other. And then there are some further lines of research that might be interesting to follow for mental effort. One, the two examples are applied tasks, and they take part in a time-constrained environment. So one of them is from Oliver Klapproth, who's modeling tasks such as you have seen in the beginning of a pilot who has several things to do, and the question that is asked is what information has been processed, especially for the auditory signals and warnings. And Marlene Schaff is working on highly automated driving, and her question is for takeover situations when people gain control over the car again, and then they may have to make a decision what to do. Has enough relevant information been gathered for an informed decision? Then individual differences would be really interesting to take a closer look on, and Kai Preuss is working on such a cognitive spatial cognition module and looking at strategies of individuals in such tasks, and these are compared with EEG data, and there's some work on the impact of task demands on time estimation. There's a strong impact of that, and a modeling approach that I conducted can explain this combination. So different tasks have a different kind of demand, and that differently impact time estimation. So I hope we have a nice discussion, and thank you for your attention.